Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. We are now at our 10th lecture of the winter 2022 semester, which I'm really excited about. And so far it's been great seeing everyone make such awesome progress with each of the projects that we've had so far. And I'm looking forward to seeing the dance routines that are going to be implemented coming up in assignment 4. But before we get to that, so we have today's lecture, which is going to be talking about robot middleware. And in particular, what we're going to focus on today is to give sort of an overview, sort of high-level introduction to some examples of robot middleware that are used in practice, so both in industry and in research. And in particular, we're going to be looking at what's referred to as ROS, which stands for Robot Operating System, which is a very common example of robot middleware, which is used throughout industry and research. And so before we get into robot middleware and ROS, I'm going to go ahead and minimize myself so that we can all see the slides. Play. All right. So on the topic of robot middleware, we're all, by now in this course, becoming familiar with this concept of trying to model robots within our computing devices, right? So just as we're seeing now with assignment 3 and as we look towards assignment 4, this slide illustrates what should be a sort of familiar concept by now, which is that we have these diverse set of computing devices, which would be like your laptop, and we want for them to be able to model our robots and the environments that our robots are existing in, right? So just like our Knievel extensile is doing, these different devices shown on this slide are modeling different robots. And so in particular, right, so each one of these different devices is able to model a unique robot. And so from the standpoint of application developers or roboticists, this kind of goal of being able to model these different robotic systems on kind of arbitrary computing devices poses a question, which is really how are we going to integrate our computing device, which is where we're going to be developing our robotic applications, with these very, very kind of disparate forms of robotic hardware that share some similarities, but are also very different. And so the answer to essentially what solves that engineering problem is robot middleware. And so robot middleware is what is going to provide an interface for our computing systems and our software side with our hardware side on the actual robotic platforms. And so that interface then is what's going to allow our computing devices to model the robots, control the robots, and interact with them. So if we look at what role this robotic middleware plays, it should look very familiar to us who are coming from a computing background from the standpoint of computing operating systems. So in particular, the real power behind robot middleware is that it provides a hardware abstraction for our applications to use. So on the right-hand side of this slide is illustrated a diagram that would be typical of the role that a computer operating system would play. So in particular, within a computing device, you have, at the highest level of an abstraction, you have the application level, right? And so here would be the programs that run on top of the operating system and can interact with the hardware through the kernel of the operating system. And so the way that the kernel provides a service for these applications is by abstracting away the actual details of the computing devices, so like the CPU, the memory, and so forth, to a very large degree. And so that's very powerful for the application developer because it enables them to essentially develop interoperable programs that could work on a diverse set of computing devices without having to worry about them kind of being able to port to these different unique pieces of hardware. And so in the context of robotics, this is the role that robot middleware is going to play. So we're going to have some roboticist who's going to develop a robot application at the high level of the hardware abstraction layer, and they're not going to necessarily want their application to be specific to one piece of robotic hardware. They might want it, for example, if it's a mapping application, to work on a diverse set of robots. And so by having a robot middleware that can interact between their robotic application and the low-level robotic hardware, they'll be able to ensure that their application has this plug-and-play interoperability with different robotic hardware. So with that high-level goal in mind for the role that we would like our robot middleware platforms to play, let's take a look at some existing implementations and some very common choices that we would see in practice. So the most commonly used example of a robot middleware is what's referred to as ROS. And so ROS stands for the Robot Operating System. So this is an example of a robot middleware platform that would be used very, very commonly in industry and in research. So we use it in our lab. I've used it. But there are other choices. So for example, LCM, which stands for Lightweight Communications and Marshalling, is an alternative to ROS, which again serves that same role as a middleware within the abstraction of from our application to our hardware. And so this is an example that you would see if you take Robotics 550 or EECS 467. And one thing that does distinguish LCM from ROS is it has as the name suggests, a more lightweight communications framework built into it. So it does have, generally speaking, more efficient message passing within it. But these are just two. There are many other examples of robot middleware, which are a few described here. So for example, the joint architecture for unmanned systems would be an older example. So if you go back to the sort of 80s and 90s, that would have been more common in that time frame. And then in addition, there also would be proprietary examples of robot middleware that are developed for within a specific company. So for our purposes in today's lecture, we're going to be talking just about Robot Operating System, so ROS, as a way of introducing a kind of a nice canonical example of how these robot middleware platforms are built and how they're used for the role that they are intended. And so focusing in on ROS, so the history of ROS we can trace back to Willow Garage, which is a famous kind of development house within robotics. And the goal for Robot Operating System was to reduce the reinvention that was needed for building up functionality within our robots. And so the kind of direction that was intended to be taken to achieve this reduced reinvention was by increasing the interoperability of software developed for robotics and the robots themselves, and also to increase the reproducibility of results both within industry and research. And so to move towards this goal of increased interoperability and increased reproducibility, the core architecture is really built on top of computer networking. And so at the kind of the high level approach was to say that within a robot operating system, we're going to have a number of different processes that are going to be running. They're going to be serving different roles within the robot operating system. And these processes are going to need to communicate to each other. And so this inter-process communication can be served using a peer-to-peer computer network. And collectively then, those different processes are going to make up the functionality and the capabilities that a robot has, right? So this could be navigation and planning, motion planning, the actual motor commands. So all of those different processes are going to be communicating with each other over this network, and then collectively making up the actual robot operating system that exists on a specific robot. And so within that, so we have this number of different processes running. The software itself within ROS is modularized as what's referred to as ROS nodes. And so we can think of a ROS node as sort of being like the core functionality of one specific piece of this collective operating system. And so these nodes are going to be communicating with each other over this network. And so the goal there was the result of this design is that it leads to increased interoperability, where by sort of standardizing how these nodes communicate, you can then use one node that was developed in one project for an entirely different project in the future. And in addition then, by having standardized packaging systems within ROS, we're able to increase the reproducibility of results by allowing for developers to share their software in a way that's modularized and easy to port to new robots. And so the packaging system within ROS is organized as a form that we're going to talk about in a couple slides. So one thing then that is important to point out is that ROS is kind of consistently under development and improvement. So it is a moving target. And so as a result of that, sometimes there can be stability issues, but that comes up just as we see in computing operating systems. One other note on this point is that the slides that we're going to be talking over today, in terms of their syntax, they are sourced from the Diamondback distribution. And since then, there's been a number of updated distribution releases. So there's just a few of them that are described on this slide. But the more recent distributions at the time of this recording are Lunar, Melodic, and Noetic. But at a high level, the concepts that we're going to be talking about today still hold within ROS. The other thing, and then I'll point out, is if you're interested and you want to look for sort of additional reading material on ROS, or if we talk about a specific topic today that you want to kind of dig into, the documentation at ros.org is pretty good. But in addition, the ROS message boards are a really great resource for finding out specific details if there's a specific kind of question or issue with the ROS that you're trying to figure out. So with that, let's see how ROS kind of fits within this development ecosystem to serve the role of the robot middleware. So once again, we have as a goal, we want to be able to have applications be developed that serve specific capabilities for our robots. So these high-level applications are going to want to be able to use external libraries. So ROS supports that. So you could use things like TensorFlow, OpenCV. Those could all be combined with a specific application that's been developed within ROS. And then what happens is the ROS packaging system provides an API to ensure that your application is developed in a way that is standardized for its communication with other nodes within ROS, and also for distribution as a proper ROS package. And so if we look at what that ROS packaging looks like, this slide kind of illustrates the kind of core components that go into ROS packaging. So at the lowest level, the most core functionality that can be built within ROS is what's referred to as a single ROS package. So a single ROS package can be thought of really as like the most modular set of functions that you would want to be grouped together. So within this, you could have a set of these ROS nodes, and so these ROS nodes can communicate internally with other nodes inside of their package, but also they could communicate with external nodes that have been developed in other packages. And in addition, within a package, you can define a set of message topics. So this would be essentially like a set of data structures that these nodes would be expecting to communicate with. And then in addition, a set of services, which we can think of as being very similar to nodes. And so within this individual package, then, the goal of distributing a single package is that you want it to be as reusable and kind of modular as possible. But to perform sort of higher level tasks, you can group these packages together into a stack and then package that stack collectively. So for example, a navigation stack would be one case where you'd have a collection of individual packages that are used within the navigation stack in order to serve that higher level purpose of navigation functions. And so at that point, once you have collected a set of these packages together and formed a stack, then we can use our kind of traditional development organization that we're used to, right? So you could have a repository where you organize these ROS stacks, and your repositories then can live within what's referred to as a ROS workspace, which is what would exist, for example, on a deployed robot system, where each of these different stacks and each of these different packages would be executed in kind of consistent behavior on a shared ROS universe, so that within this shared ROS workspace. And so if we then talk about how it is that this ROS universe is going to be executed at runtime, so we're going to have this collection of ROS nodes that are, again, we can think about each ROS node as sort of being like an individual process that's going to be running. And so these ROS nodes really are the core unit of the runtime environment in ROS. And each of these processes has access to the shared network that it can then communicate with other nodes within the ROS universe. And so each node can publish or subscribe messages where these messages are organized by topic. So you might have topics well, we're going to look at some examples coming up, but just to kind of ground it a little bit, you could have topics, for example, for image data, right? So you might be able to pass image data messages or point cloud messages or motor control command messages. And so each of these different messages would be then organized by topic so that each node is able to kind of subscribe or publish to the correct location on the network. And so within that, then, these ROS topics we can think about as being kind of the basic message structure that's used for exchanging data between different nodes. And so the ROS service, once again, yeah, so we had those ROS nodes and ROS services within a package. A ROS service we can think about as sort of being like a function-like request reply. So a ROS service is not going to be a process that's running and kind of can consistently publish and subscribe messages, but simply it'll just respond to a query if it's given one. And so the actual then data exchange that occurs within this message passing framework occurs over typically TCP or UDP. So it's a networking framework that will handle the actual data exchange. And then at the highest level of the ROS runtime, there's what's referred to as the ROS master. So ROS master is a node that's going to be used for kind of organizing the publishers and subscribers of each topic, and then routing those messages correctly. So to ground this, it's useful to look at a concrete example of what this ROS runtime is actually going to look like. So here we have on this slide shown an example of what would be sort of running and happening within ROS for a laser range viewing example. So in this particular case, so on the left-hand side here, we have a sensor. And so this sensor is going to exist on our robot, and it's going to want to interact with the robot operating system. And in addition, we're going to have some higher level application. For example, this could be like a mapping application that also exists within the robot operating system framework and is going to want to communicate with the laser rangefinder in order to process its data for the higher level application to be successful. So these two kind of components of our robot are going to want to be able to communicate. And so the way that they're going to do that is using ROS, and in particular, they're each going to have a ROS node associated with them. So the first step within the ROS runtime is there's going to be this ROS node here, which is responsible for sort of publishing the data that is read in by the laser rangefinder. So the first step that's going to happen is this laser device node, which is shown here, is going to advertise to ROS master that it has a scan topic, which it is going to be publishing, and in addition to that, it's going to specify the location on the network at which subscribers of this particular message topic can listen for messages of this topic, of this scan topic. At that point, then the master node then is aware of that, and at the same time, then you could have this application could then attempt to subscribe to this specific scan topic. So once again, so the use case here is that we have some mapping application that wants access to the data, and so the way that it's going to get access to that data is by subscribing to this scan topic, which it knows is where the data is going to be published. And at that point, the ROS master node is able to send to this particular viewer node the location on the network where the scan topic is being published. And at that point, once the viewer node has the location on the network where it can access the scan topic, it then will establish a TCP connection with the actual laser device node, and then begin essentially requesting the published data over this TCP connection. So the actual laser scan data is going to get sent directly between these two nodes over the network. And so this is, at a high level, this is the process by which different nodes within ROS are able to communicate by using this networking approach of peer-to-peer communication and data exchange. So one thing that might begin to that you might sort of be getting a sense of is that that these ROS nodes are typically can be a lot of there's quite a diversity of ROS nodes. So sometimes ROS nodes will be simply wrappers around a device, like we saw on that last slide for the laser rangefinder. Other times you might have a ROS node that's just a wrapper around some external software library, right? So for example, you might have a ROS wrapper around components of OpenCV. But other times, ROS nodes will simply be like a large set of code. We call it here a lot of code that performs some functionality that our robot is going to want to be able to actually have access to. And so to make that possible, what sometimes will happen is you have like a large code base that's going to get integrated by ROS simply by sort of wrapping the ROS API around that code base. So that's kind of a common, it's kind of like a common development habit that you might see if you begin working with ROS. So now that we have some background on ROS packaging and ROS nodes, let's look at an example to showcase how we can achieve software portability across different robot platforms by using ROS. And so the specific example that we're going to look at comes from the Brown University Robotics Lab, where they had put together, and if you're curious, the source code for this example is still online. But the demo that they had put together was to showcase a parrot drone following an AR tag. And so one thing then that we can kind of ask is how it is that ROS enables us to port this AR tag following behavior to other robot platforms. So in this particular case, the setup for our ROS workspace would be 3 individual ROS nodes. So first we'd have one ROS node for the robot itself. We'd have a second ROS node which is running recognition for the AR tag. So just to show, so this is in this image here, this is the AR tag. And then we would have a third ROS node which was running the controller for the drone to calculate its intended movements. And so in addition to these 3 nodes, within the diagram here what we're showing is the communication that would be taking place in order to achieve the AR tag following behavior. So the robot itself would be communicating, let's say, images on an image topic to the recognition node. The recognition node would communicate the let's say like found location of the AR tag in space, which it could communicate on the tag topic. And then finally, the controller here would be sending messages back to the drone, which are commanding motions for the drone to take on a twist topic. And so this is now the particular implementation of this system on the parrot drone. But one thing that's really nice about ROS is that once we've implemented this in this modular format, we can actually port it to other platforms. And so in particular, this particular group actually demonstrated this AR tag following behavior on a set of different robots. So in the 2 videos here, there's on the left-hand side is the now robot, this kind of humanoid robot following towards the AR tag, and then on the right-hand side is again the parrot drone. But this same framework actually was extended and ported to also work on an iRobot robot shown in the lower left, and also a PR2. And so this is really like the power of ROS, is that the actual like recognition and the control logic is implemented in this modular form such that it can actually port to these different robot platforms as long as those robot platforms can support ROS and can provide the proper messages on the correct topics that are being looked for within the control portion of ROS. And so to go over just a few of these topic descriptions to give a sense of what type of data ROS is compatible with working with. This is not a complete enumeration of what ROS can compute with, but this gives some examples which would have been used in that previous example. So the first case here would be like a twist message. So for any topic that is going to be that's going to be using the twist message type, the twist message type is intended to express planar motion. So you have a linear component which has essentially like a velocity in the XYZ, and then an angular component describing a velocity in the rotational degrees of freedom. Next, for example, would be a joint state message. So if you were going to implement this on a PR2 robot, in that last example from 2 slides ago, or on the slide here in the case of a fetch, you would have a joint state message defined with these data types. So you'd have essentially a set of arrays that are going to describe the full joint state at any particular time, and so each element within one of these arrays would correspond to a particular joint within the robot. So this should look familiar also to you from assignment 3. We're not following this exact same data structure layout, but in terms of the information that's being conveyed, this is very similar to what we're working with in our Knievel stencil. Another example, so on, for example, like the iRobot, there's a laser scan sensor. So the laser scan sensor has a specific laser scan message associated with it. So any topic that is going to be publishing laser scan data or subscribing to laser scan data can expect data of this type, where you're going to have a set of, for example, like the ranges, or where like this array is going to host the actual distances that are being sensed along the angles that the scanner is taking, and then you can see this additional metadata that's associated with each individual scan. In addition, then you can also store transforms that could correspond to for example, the joints and the links of the actual robot, similar to the transforms that we're storing. The difference being that in ROS they follow this format where you have specific data structures for each type and each subtype, down to the point where you have the actual XYZ and then quaternion definitions as floats. And then in addition, there's a few more. So I'm not, if you're curious about any of these specific ones, feel free to look through the ROS documentation, or we can discuss it during an interactive session. But there's also data types specific for example, odometry and also point cloud data. So point cloud data we see very frequently in mobile manipulation robots. For example, the fetch has a built-in point cloud sensor, and ROS can support all of these different data types using unique message data structures for them. All right, so now that we have seen this example of how ROS, at a high level, or sort of mid-level, of how ROS can port kind of robot applications from robot platform to robot platform as a middleware, let's now look at how it is we can write our own ROS node that could port from different robotic platforms. So to start with, let's go back and consider what it is like the output of this exercise will be. So for one thing, we're going to have to follow the ROS packaging framework, right? So the ROS packaging system is set up so that we can ensure that our project is going to be consistent across different devices. So within the ROS package system, essentially each package, like we talked about, is kind of like the basic unit. So these packages are typically going to be built by CMake, but you can use other languages, including Python, for example, supports the ROS API. And so within these packages, you'll have access to client libraries, so ROS CPP, ROS Pi, so forth. And the actual management of the package is going to be handled by an integrated build system within ROS. So you can actually rely on some built-in tools within ROS to help set up the packages, to build the packages, and to execute the packages once they've been built. And so once again, so these packages support external libraries that you could use. So OpenCV, for example, or TensorFlow. These can be integrated with these packages. So a common structure for ROS packages is shown here. For kind of just like an introduction, I'll just point out that there's a source directory, which is where the actual source code would go. You have your message definitions within a message directory. The actual CMake list text, which is what's going to control what gets built. You have one of those, and then a few others. So again, as an introduction, I would say those are probably the important ones, and we can go into more detail during the interactive session. Okay, so given that setup, so here's an example of a relatively small but still interesting package here that we can define. So in this particular case, we're going to be looking at a package that's defined using Python, and so you can see. So we'll just sort of step through this package this particular implementation, just to get a sense of how ROS can be implemented. But of course, we're not going to be using ROS directly in our assignments, but this is mostly just to give kind of an introduction to some of these tools. So the first thing within this example is we invoke Python. We have our Python includes, which gives us access to the ROS API within Python. At that point, then we can import the topic definitions. So this is going to be essentially the message data structures. So for example, in this particular case, we're importing like this twist topic that we had looked at on a few slides ago. And in addition, we're importing this sensor packet topic, which is going to give us access to some sensing information from, in this case, an iRobot. At that point, then we could set a global variable in this case. So this could be thought of as like representing the state of the robot, which in this case is saying that the bump is false. We then have kind of the real core of this particular example is starting this event loop here. So we have this function create, spin, and bump, which is going to create our ROS node, and then in addition, it's going to run through some logic that is going to get executed within the node. So the first thing that happens within this is we initialize a ROS node, which is called this create, spin, and bump, and we specify that this ROS node is going to be a subscriber of the sensor packet topic, and in addition, it's going to be a publisher of the command velocity topic, where the data type for the command velocity topic is the twist data structure, and the data structure for the sensor packet topic is the sensor packet data structure. At that point, then, what we have, if I kind of walk down here, is we then allocate so variables for this particular node to be using. So we define that it's going to have access to this global bump variable, which we had created initially, and in addition, it's going to have this local twist variable. At that point, then we have really the core of the ROS node. So within this while loop is the logic that's going to be executed throughout time. So essentially, every time that this process has bandwidth on the computing device, it's going to execute this logic here. So if we kind of look through it, it's going to check if the bump variable is true, in which case it's going to go through some logic. Otherwise, we'll have some other logic. And then at the conclusion of that, it's going to publish, we can see, this twist message to the topic command velocity that it had set up at the beginning. And then finally, it's going to wait. So this while loop will then wait before it executes again. So this then we would call the event loop. So one thing I would recommend, so maybe pause the video. I know we don't work with Python in this class too explicitly, but having stepped through that, the variables themselves should be relatively clear based on our looking at the twist topic and the twist message from a few slides ago. So I'd recommend you pause the video here and see if you can work through and try and predict what behavior this particular ROS node is going to be implementing. So I'll give you a second here. You can pause the video, and now maybe I'll kind of go through and just mention. So in this case, right? So if we kind of step through it, in this case, it's going to essentially be checking if the robot has bumped into an obstacle based on the name of this definition of this variable. If it has, it's then going to send a specific command to the robot to twist along the z-axis. So it's going to essentially turn around. Otherwise, what it will do, if it has not bumped into an object, is you can see it's going to translate in the x dimension and also rotate in the with respect to the z-axis. So in this case, it's sort of, as the name suggests, it's sort of spinning and avoiding bumps based on this logic. Okay, so those two examples kind of set up how, those gives an idea of how it is that ROS achieves this portability across different robotic platforms. And then in addition, we at least saw some example of how it is that we can implement these ROS nodes. So I'll mention we're going to have a lab section devoted entirely to implementing our own ROS node, where we'll step through that process with a live example so that we can all become familiar with ROS. But having looked at those examples, let's now consider how it is that ROS affects our ability to kind of work with these heterogeneous robotic platforms. So if we go back to what our kind of vision for robot middleware was, right? So we have this robotic developer who has a computing device that they would like to be able to interface with these different robotic platforms. And so the middleware then, which we're now considering ROS, is what allows us to interface with these different platforms. And so the key then kind of thing that we can think about, right, is not only do we have these different robotic platforms, but we also potentially have different computing environments, right? So whether it's the operating systems are different between Apple's, Windows, Android, the actual computing devices are different, or potentially your other applications that are involved within your device are distinct. These can also, potentially cause some challenges for our robot middleware, right? And so one thing that's really important to point out is that the power of ROS is that it does abstract away from all of these kind of distinct computing environments. So ROS will operate with distinct robot hardware regardless of the actual operating system or regardless of the specific computing device because of the levels of abstraction that are built into the middleware. And so that's really where the utility of ROS comes from. And so as we've been discussing, ROS is really great. It really does improve the reproducibility and the shareability of results within robotics, industry, and research. And so it has this great interoperability between different ROS environments. It's a great system for distributing packages, building packages. It has nice integration with tools to do all of those things. It's relatively easy to get started and working, and this this peer-to-peer networking architecture that we've looked at also has its benefits. But having said that, there are some trade-offs. So one thing is that ROS does have limited interoperability between different Ubuntu versions. So ROS is tied to a degree with Ubuntu. In addition, while there are some standards defined for like the build and packaging system, there are not standards and protocols defined for every platform, and so that can create some issues. And so maintaining dependencies and handling dependencies can become a challenge even with ROS. And then finally, which is like the sort of next thing that we're going to be talking about, is that ROS is not like integrated to be kind of like well suited for like client server communication, which can be a limit in some cases. But on that last point, on the topic of like client server communication, there have been some like really interesting projects. So one project that Professor Jenkins was heavily involved with, for example, is Robot Web Tools. So this is a really cool kind of extension to ROS that enables ROS to be integrated with that client server framework. So you can actually communicate with your robot over the internet, as is being demonstrated in this clip here. So you can have users actually teleoperate robots, or users remotely consume the data and the sensor information that's being taken from robots. And so this is really powerful for a number of reasons, for really like a ton of reasons. For one thing, you can have users that are remote. You could have teleoperators that are remote, right? So you can do like remote robotic surgery is one case where having robots communicate over the web is actually applicable in a very like critical use case. But in addition, it really helps with development. So you can develop these robots in a much friendlier development environment. And so in terms of the way that this actually works, so within Robot Web Tools, so it's integrated with the true internet. So what you can have is a robot that's physically located in one location. For example, let's say in San Francisco here, we have our PR2. This PR2 is going to be running ROS, and there's going to be a ROS Bridge server node that's running locally. And so that ROS Bridge server node will connect to a completely remote browser over a WebSocket and through the internet, where the browser then is itself running a local version of Robot Web Tools that's able to actually handle the conversions of message types properly. And so one thing that's kind of powerful about this, right? So now that we're familiar with JavaScript and HTML, this should look more familiar. But essentially, what we can do with Robot Web Tools and with ROS is we can actually directly publish and also subscribe to ROS topics that are remote, so that actually exist just as a web address, which is really powerful. And so here's like a few examples of ways that this can be used. So one example would be, shown here is sort of visualizing the data that's coming off of a robot. So here, I think it's a PR2 that's driving, and I believe this is Willow Garage's office. So the robot's driving through, and it's sending image data back to our web page, which is what we're visualizing, and also it's sending map data back to our web page in real time, which is what's shown on the right-hand side of that video. And so like another example of this would be, for example, this parrot drone here, which you can see is flying in real time and live streaming back the data that it's sending. But in addition to being able to subscribe to this data, our web browser can also be built in to have integrated controls by publishing messages to the drone remotely. So shown on the web browser, there are those buttons. So those buttons would actually publish messages to the ROS that's running on the robot itself and allow remote control and teleoperation. So integrating these robots and this robot operating system with browsers also has, like I said, like a number of really nice kind of use cases for visualization. So one really interesting project from out of research came from Michael Beatz's group, which is shown here. I recommend you take a look at this if you're curious about how it is that we can model some interesting like knowledge-based representations with robots. It's a really cool project that should look that you'll appreciate now, having developed your Knievel stencil with our robot operating system. And so if you're curious, then I'll point out, so this Robot Web Tools is open source as well. So you can look through the source code here. We actually will use this optionally to integrate our robots, our physical robot, our fetch robot, with your Knievel stencil if you're interested in that. And so Robot Web Tools is what we're actually going to be able to do to have your browser communicate with the physical fetch. But before we talk about that, so a couple other examples here showing how robots can be integrated with the web in a nice framework. So here's an example where the user is actually controlling the robot using these controls on the right-hand side of this demo. So you can see we're within their browser. And then the live stream results of those actions being performed is shown on the kind of throughout. I mean, the left-hand side is showing the image data that's being taken by the robot in live time, in real time. And then on the right-hand side, we're seeing like the forward kinematics running on the robot. So we're getting the joint states of each of the joints and able to visualize where the robot is in space at each time step. And so as the user takes actions, shown here, right, the robot's performing those actions pretty close to real time and then sending the resulting state back to the browser for visualization. And so an important detail of using Robot Web Tools in this way to publish and subscribe data over the internet is to consider how much bandwidth is actually used depending on the robot use case that we're considering. And so just as a brief mention of this, because it's something to consider if you do start using Robot Web Tools and ROS, is to think about how much data is actually feasible for doing some of this streaming over a network. Right, so kinematic transforms are not too data intensive; they're relatively small, right, in terms of with the type of robots that we typically work with. But when you start looking at image data or raw point cloud data, these can be really high fidelity sensors that correspondingly have very, very large data structures associated with their observations, and so those can be very challenging to stream, which can limit the use case of Robot Web Tools over the internet. But for our class, one place where we are going to use Robot Web Tools, so ROSBridge here is referring to Robot Web Tools, is when we do the optional, you can connect your Knievel stencil to our physical fetch from the Laboratory for Progress robot. And so what we're going to be able to do is we'll be able to display the real-time joint state of the fetch within your browser, as is shown in this slide. And the way that we'll do that is by using Robot Web Tools to transfer the joint state information from the fetch to your browser for the forward kinematics routine built into your Knievel stencil. So one thing I'll mention, so once again, so this is optional, and we won't do this until after winter break. But if you are interested in this, I would say make sure that your forward kinematics is compatible with the fetch example description, which is not a required feature, but if you want to do this optional sort of robot demo, then you will have to have implemented that before you can do it. And we'll talk more about this set and the scheduling of this as we get closer to break. But as a high level, one thing that we can look forward to this. And so the way it's going to work is we'll essentially connect your Knievel stencil to the robot by the robot's local network, and then we'll essentially run ROS-Bridge locally from within your browser, and then also from within the robot there will be a server running, and so there will be a little bit of code within your Knievel stencil, which is shown here, which will essentially sort of comment out or uncomment. That'll actually allow the browser to begin communicating with the fetch. But before we get to that, I just want to mention, so next lecture on Wednesday of this week is going to be starting to look at inverse kinematics. So we have that to look forward to. And with that concludes today's lecture. And so thank you for listening, and I look forward to seeing you during the interactive sessions this week.